Okay. So we understood that the finite automata could model a certain group of language, that is the regular language. And then we studied push down automata, which again was used to model another group of language, which is a broader group of language of which regular language is a subset, that is called as context free languages. Now, in the early 30s, the scientists Alan Turing and Alonzo Church were trying to identify about. They were trying to find out what are the problems that that computers could actually solve. So they came up with this Church Turing thesis, which states that any procedure or any algorithm or any problem which can be modeled with the help of a Turing machine is something which can be solved by a computer also. So there actually the statement is vice versa, which says that any algorithmic procedure that can be carried out by human beings or computer can be carried out by Turing machine. So here they are basically, that time they didn't know the power of computing, but still they were trying to find out the boundaries of these computing devices, and hence they were trying to group the problems under the category of, okay, these are the problems which can be computed or which can be solved with the help of these computational devices. And then they came up with this model called as Turing machine, wherein they say that if a problem is solved by the computer, then it can be modeled with the help of Turing machine. Rather, it makes easier to understand when we say that, okay, if there is a problem which a Turing machine can model, then definitely that is a computational problem which can be solved by a computer. Now, what is this? Okay, so this slide explains us the different classes of languages and the different automatas that are used to model these particular class of language. So we know that regular languages are modeled with the help of DFA. Then we have context-free language, which we studied in the last class. And then PDA is used to model context-free language. Then we have another group of language which the PDA cannot model, and these languages are called as context-sensitive languages. So for example, if the language is a raised to power n, b raised to power n, c raised to power n, then in that case, again, we require some more computational power, and you won't be able to solve it using a single stack maybe. Then that particular group of language falls under the category of context sensitive. And we have another machine called as linear bounded automata, which is not there in your syllabus as of now, and hence we go to a broader group of language, that is recursively enumerable language, and then we study Turing machine, which are used to model these recursively enumerable languages. Now Turing machine can model all the languages which your PDA, LBA and DFA can model. Okay, so Turing machine is considered to be the most powerful model that we are going to study. Now, what is this Turing machine model? Now, let us go back to our finite automata and the finite control and the computing power of the power of the capability of the finite automata. So it had one input tape which had a tape head control, finite control, and then the tape head used to move one cell at the time, and the tape was only a read-only tape. Then we studied push-down automata, which had a stack memory associated with it. And because it was a stack, it came up with its own limitation. That is, whatever are the limitations associated with the stack. That means you can push and pop only through one end, and the input tape associated with the PDA was again a read-only tape, and the control was allowed to move only in a single direction. Now this Turing machine, in order to model a broader class of language, definitely has to be more powerful. Okay, so what does this Turing machine has is, it has an input tape again, which is divided into cells. Each cell is going to hold one particular symbol, and the finite control of the Turing machine has a tape head which is going to move one cell at a time, but now your tape is going to be a read-write tape. So as the machine is reading from the tape, the machine is also allowed to write on the tape. However, it is going to write only one cell at a time. And another thing, in another additional capability that this Turing machine model has is basically this tape can move in both the directions. So earlier our input tape was only moving one cell ahead in the forward direction. Now the tape head of this Turing machine can move in both the direction, that is forward and backward, but one cell at a time. Now the Turing machine is again defined with the help of these components which we have seen previously, with some additional components to it. So we have Q, Q naught, F, as we have previously seen. Addition to these component is your tau symbol, that is a tape symbol. Now we have sigma. What is sigma? Sigma is the set of all the symbols which are using which the words of the languages are found. So these words can be placed on the input tape. So basically the string can be placed on the input tape. Now because you are allowed to write on the tape, the machine can write symbols which do not belong to this set sigma. So it might be the case that the machine has read some symbol A which is part of sigma, but now it is, in order to solve the problem, the machine needs to replace this A with certain other symbol, say X. So now this X is not going to be part of sigma, but definitely it is going to be part of your tape symbol. So tape symbol is basically all the symbols in your sigma plus all the additional symbols that you are going to write on your tape. Now the third component is a blank symbol B. So this symbol is basically all the cells of the tape of the Turing machine are initially blank and they are filled with some particular symbol called as a blank symbol, and this of course belongs to the tape symbol. Now whenever there is an input, so suppose the input string is of the length 4 and the tape of the Turing machine is actually considered to be of infinite length, so only 4 cells of the Turing machine tape will be filled with those 4 characters from the input, and rest of the cells will be filled with this blank character, blank symbol. Now we have a transition function. In the previous transition functions of finite automata, what we have seen that the input and the current state decides the next move, right? We are anyways not writing anything to the tape, so this was the only thing. So what we had previously was Q cross sigma gives you some another Q. In case of PDA, what we saw was input symbol along with the symbol on the stack top and the current state of the machine decides what is the next symbol, or what is the next symbol on the stack, and what is the next transition in terms of the state of the PDA. Now because we have a read write option both associated with your tape of the Turing machine, so the input symbol, so what will be the transition function? The input symbol X along with your current state Q of the machine will map to some other state Q naught. So on reading the symbol X from the state Q, the machine might go to the state Q dash and it might replace that X with some symbol Y, and D is actually the direction of the movement of the read write head. So the head can move one cell in the forward direction, or it can move to the backward direction, or we can say it moves towards the left side or to the right side. So the additional changes in the Turing machine is your tape, okay, the direction of the movement of the tape head, that what changes your transition function, and it has additional blank symbol and the tape symbols. Okay, so let us read out what is written here. The acceptability of the string is decided by the reachability from the initial state to some final state. So the final state are also called as the accepting state. Okay. Fine. So in case of Turing machine, the acceptability of the string is such that, so on processing a particular string, the machine, if enters into the final state, then we say that, okay, now accept the string and stop the processing. There is another possibility which can happen, that by if processing the string, the machine never enters into an accepting state. Okay, so after the string is completely read, the machine might end up into a state which is not an accepting state or not in final state, or the machine can never stop processing, so the machine can even enter into a infinite loop. So we will study this with respect to some examples going ahead. Any questions so far? Okay, so we'll go with the next topic now. So how do we represent the Turing machines? Again, so we have represented all our models with the help of these components that we have studied, okay, that define the particular model. Along with, we have a transition table, the transition diagram, and instantaneous description. So we've studied instantaneous description in the last lecture for our push-down automata, and we already know what is the transition table and the transition diagram. Now let us see what is the ID for a Turing machine. How does it look? So if you look at this typical configuration of the machine, so what it shows is that currently this particular string A4, A1, A2, A1 and so on is placed on the input tape, and the rest of the cells are filled with the blank symbols, that is B. The current state in which the Turing machine is Q3, and the read write head is pointing towards the symbol A1. That means the previous, all the symbols on the left side of A1 has been previously read by the Turing machine, and all the symbols to the right side are still to be processed. So how do you describe this current state of the machine with the help of ID? So we actually write it like this. If you look at the bottom here, we write it like the entire string on the left hand side of that particular symbol under the tape head, that is A1. Okay, so right now A1 is under the tape head, Q3 is the state, so we divide it likewise. So we write everything on the left hand side of A1 towards the left hand side of the ID, then we mention the state, and after the state, whatever is the remaining string, which is the leftover string which is yet to be processed, is written along with whatever is the first symbol after the state, shows that that is the current symbol under the read write head. So likewise, you can describe all the moves. So if you're asked to use a Turing machine to simulate on a particular string, you can simulate it with the help of these instantaneous descriptions. Now, how does the transition table of the Turing machine look? So the transition table of the finite automata was similar. The changes in the Turing machine is likewise that, okay, here you are going to have symbols which are going to be on the tape now. The Turing machine has a tape, so that's why we have these tape symbols here. These are the states. So if we want to read this first row, how we will read? If the current state of the machine is Q1 and B is the symbol under the tape head of the Turing machine, then we write 1 instead of B, that is we replace this B with 1, the machine enters into the state Q2 and it moves one cell towards the left. So this L represents that the tape head now moves one cell towards the left. Similarly, if 0 is there under the tape head and the machine is in the state Q1, then we replace the 0 with whatever symbol you write here. So we replace the 0 with 0. The tape head moves one cell towards the right side, one position towards the right side, and the machine enters into the state Q1. We have not mentioned what happens if the machine is in the state Q1 and the tape head is pointing towards the symbol 1. Now in this case, we have not defined any transition. That means the machine is going to halt and reject the input. Okay, so again here, in case of, this is again doesn't mean that it is a non-deterministic machine. So in case of deterministic machine, we do not define transition again for each and every symbol, that like we used to do in case of DFA. If that is not mentioned, that means the input will get rejected and the machine will halt. So we mention all the IDs and all the transitions which are necessary for processing all the valid strings. So whenever there is a valid input placed on the input tape, we should have all the transitions in such a way that that machine on processing that complete input should halt in an accepting state. Okay, similarly, if there is an invalid input placed, then in that case the machine should either halt in an state which is a non-accepting state, or it will never halt, it may go into a infinite loop. Fine. Now how does the transition diagram of the Turing machine look? So any question with the transition table, you can raise your hand if you want. Okay, so let us see the transition diagram now. So for the same machine which we saw previously, if the machine is in the state Q1 and if 0 is under the tape head, then replace this 0 with X. That means you are going to write on the tape now and move one cell right, one cell in the right direction. So first component here on the transition says what is there under the tape head. The next component says what is that you write on the tape head or in that particular cell, and then the next shows the direction of the move. Again, you can have one or many final states and rest of the things remain same. So Q1 is the initial state, Q6 is the final state, and these many transitions have been defined. Now you can get a question which can ask you, okay, obtain a computation sequence of the Turing machine M for processing a particular input string, and the input string is given. So the Turing machine is either described with the help of a transition diagram or a transition table or ID descriptions. So with the help of these description, you can take a particular string and follow the transitions and see whether when the complete input is processed, which state the machine enters into. So if the machine enters into a state which is marked as an accepting state, then in that case you accept the string, otherwise reject. So that is what is mentioned here. So initially all the symbols are placed on the tape. The tape is infinite from both the ends, so there will be a lot of blanks here and a lot of blanks here. So this one blank symbol is put here so that because now we are even moving in the left direction, how do the machine understand that it has come or reached to the leftmost end? So if while moving left, if the machine reads B, then the machine understand, okay, now you are at the leftmost end and now you cannot move ahead, something like this. Okay, similarly for the rightmost end. So here the machine is in the state Q1, the current symbol under the tape head is 0. Machine is in Q1, the symbol is 0. What has to be done? Write it with X and move one cell in the right direction. So it will be replaced by X. Here the machine enters into the state Q2, which is shown here, and then the tape head goes to the next cell in the right direction. So now the tape head is pointing on this 0. Now what happens when the machine is in the state Q2 and there is a 0 under the tape head? So you go back, you check, the machine is in the state Q2. What happens if there is a 0? The 0 is left as it is. That means it is written by 0 and the machine moves ahead. So this 0 is left as it is, and then machine moves ahead and the machine remains at the state Q2, and likewise you process the entire string. So the language acceptability by Turing machine, like I mentioned previously, a string W which is formed over the sigma is said to be accepted by a machine M. Okay, I'll take your questions, but I'll just let me finish this. A string W in which is formed using sigma is said to be accepted by M if the machine starts processing the string W from the state Q0 and over subsequent moves. Okay, this is the particular configuration which is there on the tape, okay, or which is an ID description. If alpha 1 and alpha 2 both belong to the tape symbols, and if P is one of the states belonging to the set of from the set of final state, then we accept this particular string W. Now M does not accept W if the machine M either halts in a non-accepting state. So this is the final ID, okay, after processing the entire string. So if P belongs to the final state, the machine will accept, otherwise it will reject. Or another condition with Turing machine is that, okay, it might happen that the Turing machine is not halting. Still you reject the string. Now, what was the question? Swaraj? Let me.
Ma'am, in the last example, you said that there in Q2 state, it's behaving somewhat different from Q1 state for symbol 0. Why is that?
See, this is a Turing machine which is drawn for handling a particular problem. Okay, so here from every state on every symbol, the machine can behave in a different way. There is no restriction likewise, right? Neither it was there for finite automata, neither it was there for PDA, nor it is there for TM. So I didn't get your question if this is not the right answer which I gave. So you're asking that why on 0 from Q1 we are writing with X, and why on 0 from Q2 we are leaving it as 0. Okay, because
Yeah.
the typical problem that this Turing model is solving requires this. So there is no restriction. There's no restriction that every state should behave in the similar way for every symbol. So when we'll see some example, your doubt will get more. You'll get more clarification on this question.
Okay, ma'am.
Okay. So at present, see, you don't know what this Turing machine is actually solving. Do we know? I have not written here. So we are just looking at the descriptions of the Turing machine. We are trying to understand how these transitions are drawn and labeled. Okay. So right now we don't know what this particular machine is solving. So for solving particular problem, it might require that, okay, when the machine enters into Q2, it should not replace it with X. Okay. So I have someone else raising hand.
Transition diagram,
Okay.
can we have multiple final states?
Yes.
Is it possible?
Yes, yes.
And in the transition diagram represented here, this is DFA or NFA?
Fine. Now, we are not drawing an FA, first of all. So, this is actually a Turing machine. It is not a FA, absolutely. This is, how do we decide whether a particular model is deterministic model or a non-deterministic model? So far from whatever you have studied. How do we understand this?
If one transition goes to the multiple states, then it is NFA.
Correct. So for a particular input, if the machine makes transition to multiple states, then we say that the corresponding model is a non-deterministic model. Now here, in case of PDA, when the corresponding input and the stack symbol, if the machine was making its transition to multiple state, then we say that it was a non-deterministic PDA. Similarly, in case of a Turing machine, if on a reading particular symbol from the input if the machine is making transition to two different states. So let us look at this particular diagram carefully. Do you see that from every state there is only, from what I observe is, for every symbol under the tape head the machine is making only one move, that is move to only one state. I cannot see multiple transitions. I cannot see for a particular symbol 0 from Q1. There, there are not multiple transitions shown. So this is basically for B. This one is for 0. If you see Q2, this particular move is for 0. This one is for 1. This one is for Y. If we check for Q3, this is for X. This is for Y under the tape head. This is for 0. So this particular diagram is a diagram which represents a deterministic machine and not a non-deterministic machine. We can have non-deterministic Turing machine, which we will be eventually studying going ahead. Any more questions? Okay. Now, these are some problems which we will actually see. So I'll go to some example because we have only 5 minutes remaining. So I'll take this example now. Now, this is a very classic example of Turing machine. This one basically, but let us study 0 raised to n, 1 raised to n. Now here, we can solve this problem with the help of finite automata? No. We can solve this problem with the help of push down automata? Yes. We've already solved it with the help of push down automata. We can push all the zeros onto the stack, okay, as we are reading zeros, and whenever the machine reads the first one, the machine can start popping out the zeros and check for the count of zeros and one. Now the same problem can be solved with the help of Turing machine also. However, we won't be able to solve this problem with the help of PDA, and then that's why I said that this is a classic example which can be compared. So we know that a raised to n is something which can be modeled with the help of FA. So a raised to n, b raised to n we won't be able to do with FA. We saw it with PDA. And then a raised to n, b raised to n, c raised to n, we require a Turing machine. Now we will see this example, 0 raised to n, 1 raised to n, how it is solved with the help of Turing machines. Now you are given this task or some string, and again, like I always say, you are asked to solve it with the help of pen and paper. So you take your input tape, you draw that tape, okay, on your notebook, and you place all the whatever is the example string on that each of the cells, and then you are asked that you are okay, now you can write on the tape and solve this problem. So how you will solve this? The first logic that comes to my mind is I'll take my string here. So I'll take my 0011, say I have my blank symbols which are marking the end of my string, beginning and the end of my string. So here we have the entire Turing machine filled with BBB. The current tape head of the Turing machine is at present pointing to the first symbol on the input tape. Now what can be the logic? One logic is you pick up a 0, you replace that 0 with some X, and you go ahead and try to find the corresponding one for the 0 that you have read. So I'll start here. I'll replace my first 0 with my X, okay, and I go ahead one cell at a time in the right direction till I reach my first one, and I replace this first one with my Y. Okay, as soon as I replace my 1 with Y, I again go back in search of my 0. So I'll go back and see, okay, is there any 0 more remaining in the string? I find 1, so I'll replace this 0, or I'll read 0 from the tape, I'll write an X instead of that, and then I'll search for a 1 corresponding to the 0 that I have read. So I'll search for the 1 by moving in the right direction, and I'll replace it by y. Then again this process will be continued. That means the machine will search for another 0 here. So in the search of zeros here, I won't find any zeros. So when I'm going back here, if at all there is a 0 and a 1, so when I'm going back, I've replaced this 1 with y, and I'm going back. So after all my y's have been read, I have to cross all the zeros. Okay, if at all there are more zeros, I have to cross all the zeros and then come here at this position and then replace this one with x again, and for that x search the corresponding 1 and then replace it with y. So this procedure will actually continue one cell at the time. The Turing machine will move and then keep on replacing this like this. So for every x that I write, I should have one y and replace it with, I should have one occurrence of the symbol 1 which I can replace with y. Once this is over completely, when I'm going back in the search of 0, I won't find any 0. And then if I don't find any zeros, I'll find all x's here. Okay. And then I'll come back and I'll see if there is any 1 which is remaining here. So if I find any 1 extra here, that means the number of zeros and ones were not matching. If I do not find any 1 here, now if I have only x's and y's remaining, and once I complete reading this, the tape head reaches to the rightmost end and it reads B, that means the count of 0 and 1 was same. This is what is actually described here in this diagram. So again, so I can start for another string and then we can execute with the help of the diagram. Now the machine is in the state Q0, so Q0 is the initial state. On reading the first 0, it writes an X and moves one cell right. So it will replace this with X and move one cell right. Now while it is moving one cell right, the machine will cross all the other zeros. So that's why we have this transition. The machine remains in the state Q0, and now it is actually looking for what? It has to look for a corresponding 1 with respect to the 0 which it has marked as X. So as soon as the machine finds that 1, so it even has to cross these y's which it has previously written. And then if it finds 1, it replaces it with y and then goes ahead. Finally, the last condition which is mentioned here is this one. So I think we have only less than 1 minute remaining with us. So we should actually stop and discuss this in the next class. All the examples. I think everybody has posted their attendance on the chat window. So I think I have to stop now because the time is up. So if anyone has any questions, can post it on the chat window. Okay. Thank you.